Hello, everybody. How are we doing tonight?
Hi, Professor. Doing good.
Good. Okay, and I finally remembered to hit the record button at the very beginning of the show. So I think we can get into it. Before we start tonight's lecture, which is on a totally new subject, does anybody have any questions they'd like to ask me? Alrighty. Tonight's lecture is on the subject of development or anchorage of reinforcement, which can be a pretty important and often overlooked aspect of a reinforced concrete design. Let me give you an example that I didn't build into my presentation here, but I'll give you a real world example. When I was a senior in my undergrad, we had to do a senior project, of course. And so I chose for my senior project to build 3 concrete beams. And these beams were 5 feet long, 10 inches tall, 5 inches wide. And I did 3 of them. And one of them had 2 number 5 rebars represented by the blue line here. And the other one had 2 fiberglass reinforced plastic number 5 rebars. And the third one actually had bamboo as the reinforcement. But that's not the point of the story. The point of the story is that I designed my beam with the steel reinforcement, 2 number 5s. I designed it to all the knowledge that I had as a senior of reinforced concrete design. And I had number 3 ties in this thing. I had 2 number 5 straight bar in this thing. And it was really kind of fun because I built the formwork and I bent the ties and I tied it all up and I mixed up the concrete in a wheelbarrow and poured my concrete beams. What I didn't realize was that rebar has to be anchored. And so when I loaded this thing in the test frame, it was actually a dual loading type thing. So I had a load there and a load here. And I didn't have enough length between the load and the end of the rebar to fully develop that rebar. And so as the beam started deflecting and cracking and doing all the things that beams do when you put load on them, pretty much all of a sudden, the whole thing failed. I mean, just came crashing down and it failed. I was like, wow, I thought it would have took more load than that. And in going back and analyzing it, what happened was a crack developed right here, and then that crack made its way up like this and like this. And these number 5 rebars pulled out. They blew out of the concrete without fully developing the yield of the rebar. So really what it was an anchorage failure. I did not have enough length of rebar behind the load to the end of the rebar to fully develop that rebar. So the rebar never got to its yielding stress because there wasn't enough clamped in there to hold on to it, to the yielding stress. Of course, I was just a student, but knowing then, if I knew then what I know now, the simple solution is you put a hook on here and you put a hook on here, and that hook then would have developed those rebars so they wouldn't have failed in an anchorage failure before they started yielding and crushed the concrete at the top. Okay, so I wanted to preface this whole presentation with, I've actually seen this. I've seen it happen. It was on my senior project. And I had to explain to my professor why I didn't put hooks on these things because I didn't see it coming. Okay, that all makes sense? Okay.
Yeah, it does.
Oh, great. Thank you. Okay, so a little history. Older codes. Remember, we've had the ACI code for a very long time, and older versions of the ACI code required the calculation of bond stresses. Okay, so here's a piece of rebar. Here's the face of concrete. And if I pull on that rebar, the only thing holding that rebar into the concrete are these bond stresses, so to speak. It's actually a little more complicated than that. But the friction or the interlock or the chemical adhesion, all these things that stick the rebar to the concrete, well, you have to have enough length on it in order to develop the yield on the rebar. So the way they used to do it is we would calculate what the bond stresses were and compare that to some allowable. So the bond stress, what is actually holding that rebar into the concrete, is provided by chemical adhesion. I mean, the cement, the concrete paste actually sticks to the steel to some effect. You also have a friction between the steel and the concrete. And you have the concrete, it bears on those deformations. The ribs of the rebar provide something for the concrete to actually interlock and bear on. However, bond stress is no longer computed today because the tests used to evaluate the allowable bond stress put the surrounding concrete in compression. In a beam, the concrete surrounding the tension steel is not in compression. So in other words, what they did was they put this block under compression, which would serve to clamp down on that rebar, but that's not the situation in the real beam. Our current practice is to focus on a development length, L sub D, instead of bond stress. Providing adequate development length ensures that Fy, the yield of the bar, can be developed in the rebar without pullout or splitting of the concrete. So we don't care, nor do we worry about what the actual bond stress is anymore. We just have a code allowable L sub D. And you have to provide enough steel into the concrete to satisfy the code's requirement for L sub D. If you have less than what's required, you're in danger of pulling the bar out before developing the yield. If you have more than what's required, you ought to be able to develop the full yield on that rebar. And as you know, from all the material that we've done so far, when we did our flexural designs, we always considered that the stress in the rebar is 60 KSI. We didn't think twice, it's the yield. When we developed or talked about the shear capacity and we looked at our shear ties, we looked at the yield of the shear tie. We didn't worry about if we're getting yield, we just designed using the yield. Well, now this is what we need to follow detailing wise to be sure that we can in fact develop the yield. And this is an image of the rib interlock with the concrete. The concrete actually bears on these little ribs and forms these little micro struts. Anchorage failure is generally the result of concrete splitting. Okay, so there we are. Okay, so when you try to pull the rebar out, the rebar is pushing up and away into the concrete. That would tend to split the concrete right down the center of the rebar, like so. And once the concrete splits, it will actually separate just enough that that bar can pop out. Types of bond failures. Okay, so you can have a beam with your flexural reinforcement. These little dotted circles represent a cylinder of concrete that is in tension because that bar is trying to pull out and it's radiating compressive struts in a circle. And so whichever is the weakest plane from that action, that weakest plane is going to split. So the weakest plane could be right across all 4 of these rebars, where C sub B is 1/2 the spacing to the nearest bar, less than the distance to the side or the bottom face. So if the bars have reasonably good coverage, but they're close together, the failure plane could be right across all 4 bars like shown. And again, CB is the lesser of the distance from the center of a bar or wire to the nearest concrete surface, or 1/2 the center-to-center spacing of bars or wires being developed in inches. Or in this case, the center-to-center spacing of the rebar is quite large. It's not going to tend to split this way. What it's going to do is try to split, again, concrete always takes the path of least resistance. So it's going to try to split in the nearest direction, the closest direction from the bar to the nearest face. CB to the side face, less than the distance to the bottom, or 1/2 spacing to the nearest bar. The definition of CB. Okay, so hopefully this makes sense. If the side cover and the bottom cover is adequate, then the bars will try to split right across their centers. If the bottom coverage or the side coverage is less than the spacing of the bars, then they'll try to split individually to the nearest face. One way or another, you pull on that bar, it's going to try to split the concrete unless you have enough concrete around it to develop that bar and you have enough length on the bar to develop that bar. Or you could have a splitting failure, looks like that. Again, CB is the distance to the bottom face, less than 1/2 the spacing to the nearest bar and to the side space. The tendency of concrete to split or crack is reduced by the confinement provided by stirrups or ties. Okay, so if I have these 4 bars and this beam is trying to split right across horizontally across the bars, then in these ties in here, which you probably provided for shear reinforcement, will cross that crack plane and tend to button it up or staple it so it doesn't elongate the crack and pull the bars out. So we have this thing called a transverse reinforcement index. The transverse reinforcement index per ACI 318, section 25423, K sub TR is equal to 40 times ATR over S times N. This is not SN, this is S times N. Where ATR is the total area of transverse steel. For U bars and ties with 2 legs, use 2 times the area of the tie. S is the spacing in inches of the transverse steel. N is the number of bars on the plane of splitting. If the main steel is in more than 1 layer, then N is the number of bars in just 1 layer. KTR may be taken equal to 0 for simplicity. Sometimes if you know you got it made, you can just use this as 0 and it still works fine. Okay. Any questions so far? Any questions on what it is we're trying to do here?
Yeah, I have a question, Professor.
Please.
So when you say it's the cylinder of concrete that's in tension, right?
Uh-huh.
So the bigger the steel that you use, the bigger the cylinder that it will like be in tension if they're pulling it.
Yes. Yes, it is. Yeah.
And then for the CB, isn't it? It's just like the radius from the center of the steel.
Uh-huh. Yeah. Let's go back. Okay, so CB is measured from the center of the steel to the bottom face, or the center of the steel to the side face, or from the center of steel to halfway to the center of the next steel.
Okay.
It's one of those least of deals. And it's because the concrete, again, is going to try to find the path of least resistance. So it's going to use the least resistance path.
Right. Okay, that makes sense.
Okay. But no, you hit on something absolutely. The bigger the bar that you're trying to develop, then the more tendency it causes to try to split, which means that you need more length on that bar. So the bigger the bar is, the more length you need to develop that bar. For instance, like a number 4 bar, you could probably develop a number 4 bar 12 to 15 inches. For a number 11 bar, you probably need closer to 4.5 feet or so. Okay, any other questions at this point? Is everybody clear on at least what the goal is? What are we trying to do here? Okay. So like I said, KTR may be taken as equal to 0 for simplicity. We have a limit on the effect of spacing and transverse steel. So it's not an unlimited effect. It's only effective to a point. So per ACI 318, section 25423, the confinement term CB plus KTR over DB shall not be taken larger than 2.5. And in this equation here, the KTR is this expression. CB is that least distance to the nearest face or halfway to the next bar. And D sub B is the diameter in inches of the bar you're trying to develop. Development length per ACI 318, section 25423. There's the equation. So L sub D is equal to 3 over 40 Fy over lambda square root F prime C. Remember, lambda is the lightweight factor. And then I have this psi T, psi E, psi S over, and here's this term. This is the confinement term, CB plus KTR over DB. And then this whole thing is multiplied times DB, the diameter of the bar that you're trying to develop. Where lambda is a lightweight factor from lecture 1. Psi sub t is a factor that represents the casting position. It is equal to 1.3 if more than 12 inches of fresh concrete is placed below the horizontal reinforcement or top bars, and is equal to 1.0 for all other bars. So if you have a bar that is horizontal when you pour the concrete, and there's more than 12 inches of wet concrete underneath that bar, what tends to happen is the bar separates the rock and the sand and the concrete, and it doesn't get as good of a confinement or consolidation of concrete on the underside of that bar. So they penalize you by a 1.3 factor. Psi sub E stands for epoxy. So if you have epoxy coated or zinc or epoxy dual coated reinforcement, then you have a 1.5 factor. If you have a clear cover less than 3 dB or a clear spacing less than 6 dB, it's a 1.3 factor if you have clear cover more than 3 dB or clear spacing more than 6 dB. And it's 1.0 if you don't have any coatings at all. So epoxy coated or zinc coated rebar does not develop as quickly as just bare steel. Psi sub S is a size factor. It is 1.0 for number 7 or larger bars, and it is 0.8 for number 6 and smaller bars and deformed wires. Per ACI, section 25414, the value of square root of f prime c shall not exceed 100 psi. That's a limit on that factor there. Per ACI 318.25.421, the minimum length for L sub d is 12 inches. And yeah, so that's the end of the rule. So it is what you calculate, but not less than 12 inches. Any questions? Okay, let's do the example and see.
Oh, I
Yeah,
have a question. Is
please.
there any cement that more than 10,000 psi?
Cement? No. Concrete? Yes.
Oh, I mean concrete.
Absolutely. Oh, you betcha.
Oh, because
Sure.
in our materials, I never heard of it. It's always like less than 8,000, I think. Is that like a special concrete?
Somewhat. Yeah, somewhat. It's like a super performing concrete. It's more common than it used to be, but it's still not for normal buildings. It's very, very expensive compared to 4,000, 5,000, 6,000 PSI concrete that you would normally see on projects that you might look at,
Mm-hmm.
but it's not unheard of. And it's becoming more and more common. One good example is Burj Khalifa, the tallest building in the world currently. And Burj Khalifa, I believe somewhere in the order of 18,000 PSI concrete was used on that building, which is pretty specialized, but and it also depends on your raw materials. You can't get 18,000, 20,000 PSI concrete with the alluvial river rock crud that we have,
Mm-hmm.
down here in Irwindale. Everything we have for aggregates comes out of the San Gabriel Mountains. And you try to get over 8,000 with that stuff is somewhat of a challenge. But up in Seattle, I understand where everything's this really high grade granite, they can get 12,000, 16,000, not even bat an eyelash. It's expensive, but they can get it.
Oh, okay.
Okay, so it's maybe 30, 40 years ago it was only a pipe dream, but it's being used more and more often now as high performance concrete.
Okay, makes sense. Thank you.
Okay. All right. Example number 1. Given we have 5,000 psi concrete, we have 60 grade rebar, and here's the situation. I have this 6-foot cantilevered beam off of some concrete wall or support or something. And this beam has 3 number 9s main reinforcement. The maximum moment for a cantilever is going to be right here at the face. So I need to be sure that I can develop the entire full yield of these rebars right here at the face. That's my critical section. So how much development L sub D of this rebar do I need to ensure full yield at this section? The beam itself is 20 inches wide. The center of rebar to face of concrete distance is 2.5 inches, and the center to center spacing of the rebar is 7.5 inches. Those are my parameters. So what we want is, what is L sub D? How much rebar do I need to provide to be assured that I'll develop the full yield? Concrete is normal weight. The bars are uncoated. There is more than 12 inches of concrete will be poured below the bar. So this is going to be formed up on site. And when they pour this concrete, blah, 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 when they pour it up, there's going to be more than 12 inches of wet concrete underneath these bars. No transverse steel is being provided on this beam, or none that we're care to. Actually, the transverse steel would be in this region, and it's not being provided. So what is the required development length L sub D? Solution. Well, there's our equation. That's the standard equation for L sub D. We need to pick out all these parameters. So for normal weight concrete, lambda is going to be 1.0. For top bars, because like I just said, there will be more than 12 inches of concrete poured below that bar. So the factor for a top bar is 1.3. Size of E is equal to 1 because these are uncoated bars. Size of S is equal to 1 because number 9s are bigger than a number 7. And C sub B is the smaller of half of the spacing of the rebar. So 7.5 over 2 is 3.75. Or center of bar to the nearest face is 2.5. 2.5 is going to govern. KTR is equal to 0 if we have no transverse steel. And dB is 1.128 inches for a number 9 bar. Just because I remembered it, I'm still grading homeworks, and I am still seeing students trying to calculate the area of steel by using, oh gosh, what was it? I think it was pi over 4 times the size of the rebar divided by 8. Please don't do that. We're like almost in the last week of this class and I'm still seeing that. Please stop doing that. Use the tables. The pi over 4 times the bar size over 8 is just flat out wrong, especially as you get to the bigger bars. So I looked up in the table and found that my diameter is 1.128 for a number 9 bar. So I plug in all my values. 3 over 40, 60 grade rebar, 5,000 PSI concrete, lambda is equal to 1, psi of T, psi E, psi S, CB plus KTR over dB times dB. And I get a grand total of 42.1 inches. So that's my answer. 42.1 is the minimum distance that I need to provide to develop that rebar. Any questions on this?
So you need 42.1 inches for the 3 number 9 rebars to yield?
Okay. From the face of the support, this is my critical section.
Right.
From the face of the support to the back of the rebar has to be 42.1 inches minimum.
Mm-hmm.
And technically speaking, I need that to comply with code. The code says I have to have that. So I have to have that regardless of what it does. I have to follow the code. So that's number one. Why am I doing that? Because hopefully if I provide 42.1 inches of rebar, then I will be able to fully develop the yield and the full capacity of this beam and bending without having this bar pull out of the wall.
Oh, okay. Yeah, okay, that makes sense.
Okay.
Mhm.
And in real life, I would not specify 42.1 inches. I would probably specify something like 3'8" or 3'10", right? Which is 3'10" would be 46, so 44, 46. I'll probably just call it 4 feet. Rebar's cheap compared to structural failures, right? So I probably would just call it 4 feet and be good. But technically, you have to have at least 42.1.
That's the minimum.
That's the minimum.
Okay.
Okay, any other questions on example number 1? Okay, let's do example number 2. Given I have 3,000 PSI concrete, 60 grade rebar, and here's my situation. Here's my support, And in this case, I need to have my rebar fully developed at the support. That's what I need in this case. So what is that distance need to be? If I have 3 number 7s, I have a 20-inch wide beam, I have 2.5 inches from the center of the bar to the face of the beam, and this time I have number 4s at 6 inches on center as my shear steel that's being provided here. So the concrete is normal weight. The bars are uncoated. There is less than 12 inches of concrete will be poured below the bar. It's probably going to be like 2 inches of concrete below the bar. And transverse steel is provided. Find the required development length, L sub D. Solution. There's my equation. So let's do our factors. Lambda is 1 for normal weight concrete. Psi sub T is 1.0 because it's not a top bar. There's a typo that I need to fix. Bear with me a second. Now slide 105.
Wait, what was the typo?
I'll show you.
Huh.
I'll show you. From the current slide, right there. Okay, so psi sub T is equal to 1 for top bars. It's not a top bar.
Oh,
So-
it has to be bottom.
Yeah, or I could say psi sub T is 1.0 because it's not a top bar, something like that. So I'll fix that.
Is that because it's less than 12 inches of concrete?
Yes, exactly.
Okay.
Going back to the illustration, these are the bars that I'm developing. And below that bar is like 2 inches of concrete. So that's less than 12 inches. So these are not considered to be top bars. Okay, size of E is 1.0 for uncoated bars. Size of S is 1.0 for number 7 bars. C sub B is the smaller of half the spacing of the rebar. So again, 7.5 over 2 is 3 3/4. Or center of the bar, the nearest face is 2.5. That controls. So C sub B is 2.5. KTR now is not equal to 0. I have my ATR is 2 number 4s. So that's 2 times the area of a number 4 is 0.40 inches squared. S is 6 inches on center. That was defined in the problem. That's the spacing of the ties. And N is 3 because I'm developing 3 number 7 bars. So then KTR is 40 times 0.4 over 6 times 3 is 0.89 inches. So CB plus KTR is 2.5 plus 0.89 over the bar diameter for a number 7 is 0.875 inches. That gives me 3.87. 3.87, however, is greater than 2.5. So the code says you have to cap it at a maximum of 2.5. dB is 0.875 inches as mentioned for number 7. So we go into our equation, 3 over 40 Fy over lambda F prime C. All my size are 1, but instead of this CB plus KTR over dB value, I have to use the 2.5 value. That's my maximum for that entry right there, times dB, and I get 28.8 inches. So again, I should put the illustration again at the back of it. Anyway, 28.8 inches is the minimum from my critical section to the end of the bar. And again, I probably would just round that up to 32 inches or something like that. Any questions on example 2?
So if we're not, You didn't give us like the transverse bar, the KDR is automatically 0.
Yes. Yeah. Yeah. If you don't know what the transverse reinforcement is, then you use a KTR equal to 0. And in practice, as I mentioned before, a lot of times just for simplicity, we'll just throw a 0 in there and we know the answer is conservative, right?
Mm.
So instead of 28.8 with without that KTR, maybe the answer would have been 32 inches. Okay,
Oh,
put a 3-foot bar in there. Who cares?
because the LD will be bigger, right?
Right, right.
Okay. Okay, that makes sense.
Okay. All right. So what we just talked about was the development of a straight piece of rebar in tension. So the bar goes straight into the concrete and we're trying to pull it out in tension. Now, as I mentioned about my senior project, if I had analyzed my anchorage situation, I would have seen that I did not have the required anchorage that I needed for that rebar, obviously, because it failed. So what I could have done, what I should have done, was bent those number 5 bars with a hook on them. And the hook develops a piece of rebar much quicker than just a straight piece of rebar. So if you don't have enough room to get what you need on a straight piece of rebar, then you can use a hook bar. So to reduce the required distance to develop the reinforcement, hooks may be used. And so here's a hook. This is my critical section. This is the part of the rebar that's being pulled on. And this is what a hook looks like. So the tail of the hook has this minimum requirement of 12 dB, but the extension of the hook into the concrete is what we calculate with LDH. Where ACI 318 section 25431 specifies LDH as the greater of A, B, or C. Now, before we do that, let's talk about this hook right here. CRSI puts out these tables where they kind of figure this stuff out for you. So the hook extension here from the flat of the bar to the end of the hook is usually how we specify it. And these are tabulized here. So you can see for a number 4 bar, you need an 8-inch hook. But for a number 11 bar, you need a 2-foot long hook. And so it grows exponentially as you get into the bigger bars. Okay, so that's this 12 dB part here. That's just kind of standard detailing, but you still need to calculate LDH. So LDH is the greater of A or B or C, where A is this equation here, and it looks kind of like the one we just did, but it's a little simpler. It has the yield, it has a psi E, psi C, psi R over 50 lambda square root of F prime C times dB. B is much simpler. You have to provide at least 8 times the bar diameter. And C, never can it be less than 6 inches for any reason. Lambda is the lightweight factor from lecture 1, which is 0.75 to 0.85 to 1.0 for normal weight concrete. Psi E is this epoxy factor, but notice it's a different epoxy factor. The last psi E for a straight bar, we had a 1.5, a 1.3, and a 1.0. For a hook, we just have 1.2 for epoxy coated or zinc and epoxy dual coated of reinforcement. And we have a 1.0 for uncoated or just plain zinc coated or galvanized rebar. So this is a totally different explanation, totally different factor than the same psi E that we use for straight bar. Psi C is a coverage. It is 0.7 for number 11 bar and smaller hooks with a side cover normal to the plane of the hook greater than 2.5 inches, and for a 90-degree hook with a cover on the bar extension beyond the hook greater than 2 inches. And it's 1.0 for all other bars. Size of R is confining reinforcement, which is 0.8 for 90-degree hooks of number 11 and smaller bars. If they are enclosed along LDH with ties or stirrups perpendicular to LDH at a spacing S less than or equal to 3 dB, or enclosed along the bar extension beyond the hook, including the bend within ties or stirrups perpendicular to L extension at S less than or equal to 3 dB. Equal to 0.8 for 180-degree hooks of number 11 or smaller bars enclosed along LDH within ties or stirrups perpendicular to LDH at an S spacing less than or equal to 3 dB. 1.0 for all other cases. What are we talking about? If you have a hook, and in this region where the hook would try to straighten itself out and blow the concrete off, if you have all these ties of a spacing less than or equal to 3 times the diameter of the bar you're developing, then you satisfy number 1. If you have these ties at a spacing less than or equal to 3 dB within the extension of the hook, you satisfy number 2. Otherwise, just use 1. Any questions on this? ACI 318.25.433, if both the side cover and the end cover are less than 2.5 inches, then A through C apply. A says the hook shall be enclosed along LDH with ties or stirrups perpendicular to LDH at S less than 3 dB. That's this situation. The first tie or stirrup shall enclose the bent portion of the hook within 2 dB of outside of the bend. That's this dimension here. And size of R shall be taken as 1 in calculating LDH in accordance with 25.431. So this is what this is saying is if you're trying to develop a hook of rebar and the coverage outside the plane of the paper is really thin and the coverage on the back of the hook is really thin, that hook is really going to try to just blow the concrete off and not develop itself. So you really got to put a lot of steel around it to confine it. So when you blow the cover concrete off, it still has concrete that can develop the bar.
Can I clarify something, Professor?
Yeah.
So for the first one, you were talking about the LDH, and when the stirrup is perpendicular, you use that first what do you call it?
Well, paragraph 1.
Yeah, okay.
Okay,
And then
that's this one.
right. And then for the second one, you were talking about the L extension now.
That's this hook right
Right.
here. Mhm.
And then the LDH is the top part, right?
LDH is still the distance from the back of the hook to wherever your critical section is.
Oh, okay. Yeah. Okay, that makes sense.
Okay.
Mhm.
All right. ACI 318, table 25.3.1 gives the straight extension of the hook as a minimum of 12 dB. ACI 25.4.10.1 and 25.4.10.2 allow a reduction of the development length of straight, hooked, headed reinforcement, we haven't talked about yet, but not less than the applicable minimums for excess reinforcement. So LD, LDH, those two we just talked about, and LDT we'll talk about in a sec, can be reduced by a factor of AS required divided by AS provided unless you are non-continuous supports at locations where anchorage or development for FY is required or where bars are required to be continuous. for headed and mechanically anchored deformed reinforcement, and in seismic force resisting systems in structures assigned to seismic design categories D, E, or F. So let's go back. So these are 4 situations where you cannot reduce the required development length. What this is saying though is, say like I'm providing 4 square inches of steel, but I only really need 2 inches of steel at that location. So why do I need 4 feet of development? I don't even need the full development of the bar. So it does allow you to go back and reduce that length a little bit if you want to, because you have more steel than you need, but not if you're in one of these 5 situations. Okay, example number 3. Given 4,000 PSI concrete, 60 KSI steel, and we're back to our cantilevered beam situation. I got the 3 number 9s, I got the 6-foot cantilever, but now I've got a hook on my bar instead of the straight bar of example 1. Same spacing applies here. Concrete is normal weight, bars are uncoated, bar cover is greater than 2 inches to the side. You can see the side coverage is about 2 inches and the back coverage is infinite. Transverse reinforcement does not meet requirements for confining reinforcement. So if I do have steel in here, it's not enough to meet those requirements. And what is the required length of my hook? My hook length here for this situation. Solution. There's my equation. And I find my factors. Lambda is 1.0 for normal weight concrete. Psi E is 1.0 for non-coated bars. Psi C is 0.7 for my coverage requirements. Psi R is 1 because I have an unconfined bar. dB is 1.128 for a number 9 bar. So I take my equation, I plug in my yield, psi E, psi C, psi R over 50 times lambda times square root of F prime C times dB is 1.128, and I get 14.98 inches. My second requirement, LDH, has to be at least 8 times dB, which is 9 inches or 6 inches. So of these 3, the 14.98 does control, and I would use 15 inches as my hook minimum. Isn't it interesting to note, though, for hook bars, there's no such thing as a top bar. There's no psi T for top bars for hooks. That's just the way they wrote it. Any questions? Example 2. Okay. Let's talk about development of headed reinforcement. To reduce the required distance to develop reinforcement, you may use heads instead of hooks. So headed reinforcement, it's a straight piece of rebar, but it has a head that is either forged into the bar, or it's welded to the bar, or it may be screwed into, like the bar has threads and the head has female threads, and they fasten to each other. Code doesn't care how it's attached. It could be forged, or it could be welded, or it could be threaded on, doesn't matter. And this head here, in order to pull the rebar out of the concrete, you'd have to blow out a big old cone of concrete or crush the concrete directly under the head of the rebar. But you still need some development length between your critical section and the backside or the bearing side of the head. So LDT is measured to the front face or the underside of the head to your critical section. ACI 318, section 25.441 specifies that heads can be used when all the following conditions are met. The bar shall conform to section 20.2.1.3, which basically says that it's an A615, A706, or an A995 rebar. The bar Fy shall not exceed 60,000 PSI. Okay, so you can't use headed rebar if it's 80 KSI bar. The bar size shall not exceed number 11. So up to a number 11, but not 14 or 18 or now 20s. The net bearing area of the head, A bearing, shall be at least 4 times the area of the bar itself, at least 4 times. And the concrete has to be normal weight. You can't use lightweight concrete with headed reinforcement. Front cover for the bar shall be at least 2 dB. Clear cover for the bar shall be at least 2 dB. And clear spacing between bars that are being developed by heads shall be at least 4 times the diameter of the bar. ACI section 25442 specifies LDH as the greater of A, B, or C. A is the equation. You notice they are getting progressively easier here. So LDH for headed rebar is 0.016 Fy psi E over square root F prime C dB, or 8 times the diameter of the bar, or 6 inches. Psi E is for epoxy, and it's 1.2 for epoxy coated or zinc and epoxy dual coated reinforcement, 1.0 for uncoated or zinc coated, which is galvanized reinforcement. F prime C and A here shall not exceed 6,000 PSI. Here's an example of a commercially available headed rebar. This is the rebar. They forged the head right onto the rebar, and you order these in certain lengths. And down here, we have the area of the steel, and we have the diameter of the head, but they didn't list the area. But the area of the head has to be at least 4 times the area of the bar. Here's a different form where this one has male threads attached to the rebar or welded to the rebar. And then you have female threads that thread into the head and provide a headed reinforcement that way. Okay. Any questions on headed rebar? Okay, so now we have this thing called welded wire fabric. Has anybody heard of, seen, touched welded wire fabric? In the concrete world?
No.
Okay. So welded wire fabric is a reinforcement style, but instead of rebar, these are wires. And the wires can either be dimpled, which makes them deformed, or the wires are plain, which means they're just absolutely smooth wire. And a smooth wire would just pull right out of concrete. There is very little to stop a smooth wire from just pulling out of concrete. So a welded wire fabric has these cross wires. And the cross wires, every place that a cross wire comes in contact with a main wire, they're welded. They're like resistance spot welded. And so generally these come in mats. So this main wire here would be a certain size at a certain spacing, 6 inches on center, 12 inches on center. And then the cross wire would be a certain size, and it too would be at a certain spacing. And so the manufacturer, the fabricator of these welded wire mats, takes the design information and will build for you, for your design, mats. They could be 10 feet wide, 20 feet wide, whatever, the design calls for. Okay. But to develop a smooth wire or even a dimpled wire, you need a cross wire. And so if this bar tries to pull out of the concrete, it's got to either fail the weld on this cross wire, or it's got to pull that cross wire out with it in order to pull this bar out. So starting with deformed wire reinforcement, you have this LD dimension from your critical section to the back of the wire. And ACI 25462 specifies that LD is found from ACI 318.25.4.2 or 25.4.2.3. LD for straight rebar covered first in this presentation. So it's either covered by the same provision that we did for straight rebar, but then you multiply it by a wire factor psi sub W found from 25.463 or 25.464. So you basically find the LD from the same equation we did for a straight rebar, but then you can generally reduce that LD because you have this cross wire that really helps out. ACI 25463 states that if you have at least one cross wire located at least 2 inches from the critical face, then psi sub W shall be the larger of Fy minus 35,000 over Fy, or 5 times dB over S, where S is the spacing of the wires being developed, right? Because it's not usually one wire, it's usually a regular spacing of wires. ACI 25464 states that if you don't have a cross wire, or it's not in this region where you need it to be, then psi sub W is equal to 1, and the development of this deformed wire is really just the same as the development of the same size of rebar. ACI 25462 allows for epoxy-coated rebar, then psi E is equal to 1 as well. Okay, now here we have a different situation. This is for plain wire reinforcement. The last one was deformed, now this is for plain. Main difference is you have to have true 2 cross wires instead of just 1, because the plain has very little development of its own. ACI 25471 states that true cross wires are required, and ACI 25472 gives LD as the greater of 0.27 Fy over lambda square root F prime C AB over S, or the spacing of the cross wires plus 2 inches. It's interesting. So it's the greater of these two, where S is the spacing of the wires being developed. So these wires are on a regular spacing, and your cross wires have a spacing as well. Okay, any questions on welded wire fabric? All right, why don't we take a 10-minute break and let's reconvene at, well, let's say 6:10, if that's okay.
I have a question, Professor.
Sure.
So the wire fabric that you were saying,
Uh-huh.
is that like a mesh?
It is a mesh. Uh-huh.
So you put that either, oh, it has to be at the top of the steel, like the rebar that you were trying to reinforce steel, and then you put the mesh on top of it?
No. This is the development of the mesh itself.
Oh, okay.
It's the development of the wires, because you can use a welded wire mesh as reinforcement.
Mm-hmm.
For example, we use it in our business all the time as the reinforcement for a 2-inch thick concrete flange on the double T member. So the only reinforcement in this 2-inch flange is a welded wire mesh. These wires here are much smaller than even a number 3 bar. They're smaller than the smallest rebar. But this flange, when we deliver the double T's to the job site, before they pour a cast in place topping slab on top of that flange, the flange is just a 2-inch thick piece of concrete hanging off the side of a double T stem. So if you step on this, you got to have reinforcement in here to resist that moment of somebody standing on it, or else this chunk of concrete just falls off, right? So we have to be sure that we've developed this mesh. And we do that by having these cross wires welded to the mesh. Now the cross wires could be on the top or on the bottom, it doesn't matter. They just have to be welded to this wire and at least 2 inches away from the critical section.
Right. Okay. And then one more. So why do we use the hooks for, like, in example one for the hook, and then I tried to compare it to example one for the straight one.
Uh-huh.
So I noticed that the space, the LD is much shorter, right?
For the hook, yeah,
Right.
yeah.
And then, so why do we need to, like, is that because to make the LD shorter? Is
Yeah.
it like economically, or?
Well, think of this situation. This is a concrete column, and we have a little protrusion off of that column that we call a corbel. That's called a corbel. And the load comes into this corbel. This distance of the column could be 20 inches, 24 inches. So if I have number 9s in here, I don't have enough room to develop a straight number 9. And I would have a head on the front of the number 9 there. So I have to use a hook because there's no concrete there to develop a straight bar. A straight bar, the development length of a straight bar would be way out here on the back side of the column. I can't do that. So I have to use a hook.
Can you use like a headed rebar?
You could. Yeah, you could use a double-headed. You could put a head back here, and that would
Oh,
basically do the same thing.
as long as it follows the code.
Yep.
Okay. So we have like different options on how we design it, right?
Depending on the geometry of what you're doing. Yeah.
All right. Okay, that makes sense. Okay, thank you.
Okay. 613 now. Let's rejoin at 613. Okay. Let's see if we can wrap this up. All right. So, were there any questions? Any other questions on what we've done so far? Okay, we are now moving into the development length of compression steel. Okay, so what we've done so far is grab that bar and try to pull it out of the concrete. But what if you take that bar and try to shove it into the concrete? How much development length do you need then? And it is less than the tension, but it still can be a considerable amount. So we call that LDC for compression steel. For deformed reinforcing bars and deformed wire and compression, ACI 25492 gives LDC as the greater of, and here's our equation, LDC is Fy psi r over 50 lambda square root F prime C, or 0.0003 Fy psi r dB, or 8 inches as a minimum. We have a lightweight factor from lecture 1, 0.75 to 0.85, or 1.0 for normal weight concrete. Psi sub r is confining reinforcement, and it's equal to 0.75 for reinforcement enclosed within any of the following: a spiral, a circular continuously wound tie with dB greater than a quarter inch and a pitch less than 4 inches, a number 4 bar or a D20 wire, ties in accordance with 2572 spaced at less than or equal to 4 inches on center, or hoops in accordance with 2574 spaced at less than 4 inches on center. So if you got a bunch of steel in here, then when this bar is trying to torpedo through the concrete, it can't split the concrete because all the steel is holding it together. If you don't have all that steel, then psi sub r is 1.0. Okay, that was pretty simple, right? That's it for compression steel. Now what we're going to talk about is reinforcement cutoff points. And this is where many times in design, you may need all this steel at your point of maximum moment. So like in this case with the cantilever, your point of maximum moment is right here against the wall. So whatever steel you need all of it right here. But the moment maybe back here someplace is only half of the moment at the wall. So why do I need to carry all this steel all the way to the end if I don't need it anymore? And the same applies for just a normal simple span flexural beam, where maybe you don't need all the steel all the way to the end of the beam. You just need all that steel at the point of maximum moment at the center of the beam. Same idea. So if I have a moment diagram that looks like this, MU, ACI 318 section 973 allows bars to be terminated when they are no longer needed for moment resistance. So as I said, your maximum moment is right here at your support, but somewhere out in here, the moment may be a fraction of the maximum. We can start by plotting the phi-min diagram on top of the MU diagram. Okay, so what we did is for bars A and bars B, we calculated the flexural capacity at this point here, and then it's constant, right? Because the bar area is constant, D is constant, so phi-min is going to be constant all the way out. But then what I did here is at some point from the end of the bar to LD into the bar, these bars are not fully developed. So I went linearly from 0 development right at the end of the bar to LD at the full development of the bar. So you have a linear development of capacity as you go from 0 development to full development. From the overlay of phi min and the MU diagram, you can see that phi min is greater than MU at all points. So at all points, the blue is greater than the red. My phi min is greater than MU at all locations. At the termination of the bars of A and B, we have a linear progression of strength that the bars are developing within the LD length. Okay, so that's basically what I just said. But if the bars are terminated at the end of the beam, then it takes L sub D. That's the first straight bar in tension L sub D that we learned in this presentation. It takes a distance of L sub D to fully develop those bars. For most of the span, phi min is much larger than needed. Therefore, some bars could be terminated early. I mean, look right here. This is my demand, and this is my capacity. So we can look at the point where the moment is half of MU and terminate half my bars where they're no longer needed. So this point here is half of my design MU. So if I project that up on here, I could terminate my bars. Theoretically, I could terminate my bars right there, and I have my capacity just in bars A. However, code doesn't let you do exactly that. Theoretically, we could terminate the bars exactly where they're no longer needed, but ACI 318 section 9733 specifies that the bars must be carried at least a distance of D or 12 dB, whichever is greater, past the point where they are no longer needed. So at the halfway point of MU is where theoretically I don't need them anymore. I need to carry them beyond that point by the greater of D, which is the depth from the center of the bar to the compression, or 12 times the diameter of the bar, whichever is greater. So I need this little extra bit there just to cover it. Then we construct a revised phi min diagram that looks like this. Okay, so at this section, all I have are my A bars. So this is the phi min for my A bars only, and it takes L sub D to develop those A bars. Then I cut off my B bars at this location, so they start developing the B bars, and then once they're developed, the A bars are already developed. Once I develop my B bars, then I get the full phi min of all my steel at this point. You can see then I still have phi min greater than mu at all locations, but this is a more efficient design, not quite as wasteful on my steel. And we confirm the phi min diagram covers the MU diagram at all locations. Remember how many times have I said when you're doing your flexural designs that you design your rebar and your D and your H and all these things, but you always, always, always have to check that phi min is greater than MU. Well, that's what this diagram is doing, only it's not just doing it at one location as you would be doing with phi min greater than mu. It's actually graphically shown that phi min is greater than mu at all locations, which is really what you need to do. You need to confirm that at all possible locations that your capacity, your allowable capacity, is always greater than your demand. But by doing this cutting of bars, you can actually save quite a bit of steel in a typical building by doing this strategically. But as long as you follow code and make sure that you've always got yourself covered. ACI 318-9735 gives further restrictions on the cutoff points for flexural reinforcement, stating that at least one of the following must be satisfied. First of all, and before you can cut your bars, VU has to be less than or equal to 2/3 of your phi VN. For number 11 bars and smaller, continuing reinforcement provides double the area required for flexure at the cutoff point, and VU is less than 3/4 of phi VN. Stirrups or hoop area in excess of that required for shear and torsion is provided along each terminated bar or wire over a distance of 3/4 D from the termination point. Excess stirrup or hoop shall be at least 60 BWS over FYT. Spacing S shall not exceed D over 8 beta B, where beta B is the ratio of reinforcement cutoff to the total area of tension reinforcement at the section. What they're really worried about is the shear on a beam has the effect of elongating the requirement of tension. So if your moment diagram would imply that you need a certain amount of steel at any given point to satisfy the moment, the shear requires that that point pushes back towards the support a little bit. And so this prescriptiveness is just covering that. ACI 318-9738 gives further restrictions on bar cutoffs and continuation of rebar at supports and inflection points, which are beyond the scope of this course. Okay, any questions about bar cutoffs?
So it's like you gradually cutting the required steel needed, right?
You can. You don't have to, but you can, yes.
And as long as your phi phi mn is greater than mu, right?
That's what really matters, that phi mn is always greater than mu, and you construct that phi mn diagram like I did with the consideration of when you cut a bar off, you don't instantly get that full capacity of the bar 1 inch over. It gradually builds up to its full capacity.
Right. And I also have a question about when you compress the steel that you were saying earlier.
Uh-huh, yeah.
So when we are compressing the steel, we don't generate like the cylinder compared to the tension. Is that right?
No, actually you do. It's just, no, actually you do. You do generate the cylinder just like in tension. But it's in the opposite direction. But it's still a cylinder of tension because when you pull the bar, you have these little micro struts that are radiating out from the bar. And those struts are compression struts going at an angle. And so there's a horizontal resultant of that angle that puts that cylinder into net tension.
Mm-hmm.
Well, exactly the same mechanism happens if you try to push the bar instead of pull the bar. It's just that the micro struts are going in the opposite direction, but they still create that tensile component.
So technically like splitting the cylinder too.
Yes,
Okay.
yes. Yeah, so if you pull a rebar, you split the concrete that's trying to hold the rebar. If you push a rebar, you still split the concrete that's trying to hold the rebar.
Right. And then there's no like how do I say it? Like the hook, it's just a straight one when we were compressing. Does that make sense?
I think what the code says is the hook doesn't help you with compression. The hook is only for tension.
Yeah,
So,
okay, yeah.
so if you have bars and compression, it doesn't mean you can't have a hook. It just means that the hook doesn't really shorten the length it needs to develop the bar and compression.
Okay. I think that's it. Yeah.
Okay,
Okay, that makes sense.
all right. Rebar splicing. Okay, there are many cases where rebar must be spliced, either because of staging or construction, or even maximum available length of rebar. We do precast elements quite often that are longer than 60 feet long. And the practical limit on trucking of rebar is about 60 feet. So if the precast member is longer than 60 feet, we have to splice rebar together. You also use rebar on concrete floors, and many times a building is several hundred feet long, and you're not going to find rebar several hundred feet long, so you have to splice it. Reinforcement can be lap spliced, mechanically spliced, or spliced with welded connections. Lap splicing is covered here. Okay, so here's the idea. You got a piece of rebar, but you ran out of length. So you're going to put another piece of rebar really close to it, but you have to overlap one from the other so that you don't lose any capacity as you're going through this section. In other words, if you just put two pieces of rebar with like a 1-inch lap, they'll just rip apart. The concrete will crack and split right down the middle, and both pieces of rebar will just pull out. There's no development on them. So you have to have proper development of one rebar relative to the other rebar. ACI 318.25.521 defines the two types of splices, either as type A or type B splices. For a splice to qualify as a type A, the area provided over the area required must be at least 2.0 at the location of the splice, and no more than 50% of the total reinforcement is spliced at one location. So you can't splice your entire bundle of rebar capacity. You got to stagger your splices. If a splice doesn't qualify as a type A, then it is by default a type B splice. For type A, LST equals the greater of, that's the lap splice distance, LST. It is either 1 times LD, 12 inches, or 12 inches. For type B, LST equals the greater of 1.3 times LD, or 12 inches. This is usually 1.3 times LD. That's what we follow almost most of the time. Excuse me, I think I'm getting the hiccups. Go away, hiccups, go away. ACI 318, section 25522 states for bars of different sizes, LST shall be based on the larger of the two bar LD lengths. So if you're splicing a number 9 and a number 11, then you base your LD on the number 11 bar. Oh, that was rather dramatic. That is the end of my presentation on rebar splicing. Do we have any questions? Okay, I do thank you for the questions that we had. Those are very interesting. You can't possibly cover everything in a presentation like this, so I do appreciate comments and questions. And we are drawing towards the end here, folks. After today's lecture, let's just do a quick review here. Today was bond development of reinforcing bars. Homework 8 was assigned today. Homework 7 is due tonight. On Thursday, we're going to start talking about footings. On next Tuesday, we're going to talk about retaining walls. And the last class lecture is really just meant to cover any overflow from these two lectures and or to spend some time to talk about the final exam. Again, the final exam is on Tuesday, August the 10th from 5 to 7:05 p.m. And we are almost there. So any questions for me for tonight? Any questions at all? Okay, so we will close for tonight. I thank you all, and we will see you on Thursday.
Thank you, Professor.
Thank you.
Thank you, Professor.
Thank you. Have a good one.
You too. Thank you.